my pleasure to introduce a truly remarkable RL researcher, Emma Brunskill, an associate professor at Stanford University. What makes Emma remarkable is her rare blend of theoretical rigor and impactful real-world research. On the theoretical side, Emma's work is characterized by thorough, principled analyses that help us to understand what makes RL problems hard and which informs the design of efficient algorithms. As an example, back when we only had ideas and empirical evidence about what makes options help and how they can help, it was Emma who offered a formal proof that clarifies when and how options can accelerate learning. But Emma's work doesn't stop at theory. She offers a long line of work investigating how RL algorithms can be used in education. For example, to improve intelligent tutoring systems. What's particularly noteworthy about her dedication, noteworthy is her dedication to deploying these systems in the real world, working with real students and navigating the challenges of applied RL to create meaningful practical advancements. So today we're fortunate to have Emma here to share her perspectives. Let's welcome Emma Brunskill.
Well, I'm delighted to be here. I think it's amazing to be at the first Reinforcement Learning Conference, and I really appreciate everyone sticking with me through the awful mid-afternoon period when we all wish we were drinking coffee. So I'll try to keep this engaging. And what I want to talk to you about today is about how do we advance science and data-driven decision-making in noisy worlds. So this morning's talk was wonderful from Dave Silver, and he talked about this incredible result that came out of DeepMind recently, where they achieved sort of silver level math Olympiad performance. And this is really quite phenomenal. It meant that they had an RL-based system that was achieving roughly in the top 10% of the 600 students that took the math Olympiad, which are already representing some of the top math students in the world. So this is really a phenomenal achievement. But the statistic that tends to keep me up at night is more on the other side, which is in 2022, the National Assessment for Educational Progress did their sort of annual check-in to see how 8th graders in America were doing on math. And unfortunately, about 25% of those 8th graders were below even basic levels of performance. And in America, that means that's roughly around 900,000 students that can't do even basic levels of mathematics. So I was curious about what that would mean. You know, what sort of math is it that humans are not able to do? And what sort of math do we have AI being able to do? So I looked up the problems, and on the right is one of the problems that was on the Math Olympiad this year. This is one of the 6 problems. And you can read it for yourself. This is determine all real numbers alpha such that for every positive integer n, the integer alpha plus 2 times alpha is a multiple of n. And then I tried to find the most similar thing that I could find on the 8th grade math assessment, which had to do with simplifying basic integer expressions. Now, Dave this morning gave you a challenge that if you didn't want to listen to his talk, you could try to solve the problem. I imagine that this will be very fast for most of you for the problem on the right. Okay, but this is unfortunately an example of a problem that about 25% of American students cannot solve. So this means they're not at that level to be able to solve that problem there. So this really concerns me because I believe in a vision where we think of AI augmenting human capabilities. And I think as all of us in the audience know how to solve that problem on the left, we really need to make sure that we're inviting people with the capabilities so that they can achieve their goals and their ambitions and create the sort of system that David Silver was talking about. So I know I'm dating myself a little bit, but I really love this moment in a movie called The Matrix that came out maybe about 25 years ago now. And in it, perhaps it's particularly appropriate to be talking about this now, humans are fighting against a super intelligent AI. You can think of that what you will, but in any case, that's actually just a side note to this story, which is there's a moment at which one of the main characters, Trinity, needs to learn a new skill. And the skill she needs to learn is how to fly a helicopter. Now, for any of you that have ever tried to ride a bike or learn to fly an airplane or learn to drive a car, you know that it typically takes on the order of days to weeks to months. But in the movie, what happens at this point is Trinity just downloads a program into her brain, and about 30 seconds later, she can fly a helicopter and help defeat the super intelligent AI. So I think of this vision of thinking of how radically better we could be at a lot of the things that we want to teach people how to do, or a lot of the skills and capabilities humans wish they have, as being a really inspiring view of what might happen if we could couple together human ingenuity and AI. Now, when we think about doing this, similar to what Dave was talking about earlier, we need to be able to go beyond even the best of human level performance. Because while we have some great ideas in healthcare and education and other areas, we are not at optimal performance yet. And the way that we need to get there is to think about how do we use these sort of data-driven methods to figure out from experience and real evidence to try to accelerate how quickly we can learn skills so we can be like Trinity, to do things like help treat cancer radically better, and to create social systems that support us all. And so to do that, I and many others, including many people in the audience, have been really thinking about how do we accelerate data-driven decision-making for the purposes of societal good. And so what I want to do today is I want to talk to you a bit about some different efforts, 3 sort of different strands, of ways we might make progress towards trying to accelerate how quickly we can use data to drive better decision-making. So the first thing I'm going to talk to you about is getting better data. I just want to start here by reminding us that getting better data can sometimes radically accelerate learning. So this is a curve comparing exponential versus polynomial growth. And for those of you who've taken sample complexity results in reinforcement learning, you're probably aware that sometimes we really can radically reduce the amount of data we need to learn to make good decisions. Now, this is important for many reasons, but the idea of sort of strategic data gathering in order to answer scientific questions or optimize better comes up in a huge area of huge numbers of fields. So it's certainly true in reinforcement learning and multi-arm bandits, but it comes up in things like active learning, experiment design, and even things like hypothesis-driven research. So it's important in many, many cases, and there's really an incredible legacy of work in this space. But what I want to argue to you today is that we're not done. So despite this incredible legacy, these questions continue to be open, and there continues to be a lot of really pivotal work that we can do in this space. So let me give you a particular really, really simple example of somewhere where I think it's not solved and it has important implications. So let's think about contextual bandits. Now, contextual bandits I think of as just being under the umbrella of reinforcement learning, which perhaps according to Andy Barto covers everything anyway. So let's just think about contextual bandits, and let's think about a particular scenario where we get to choose both the context, or the state, and the action. And the question is, what data should we gather in order to learn a good policy? So I'll be a little more precise. We're going to try to think about a really small scenario here to think about characterizing it formally, but I will motivate it from some real examples. So let's imagine in this case that you have some sort of population. It might be different ages, it might be gender, it might be a lot of other things. And each of those states or contexts has some population proportion. And you can sample a set of states and actions. And once you get that data, you can use it to learn a good state-dependent or context-dependent policy, just like what we're normally doing in reinforcement learning. I'm going to assume for now that we just have 2 actions and a small finite set of states. So that's going to mean that we're not going to need function approximation. We're going to be able to just use very small amounts of data and very simple ways of counting and estimating performance. So in particular, I'm thinking about the following scenario. I'm going to try to design an algorithm so that my computer is going to go off and say, these are all the states and actions that I want to sample and get information about. And then my scientific experiment or people, et cetera, are going to give me a reward sample for each of those different context action pairs. And once I do that, I can just average the performance for each context and each action to get a reward. So again, I'm assuming the case right now where my state space is pretty small and my actions are just 2, so I can just average. I don't have to do anything complicated in this setting. And then I'm going to say that the policy that I'm going to use in the future is just going to be the argmax of that reward function. Again, this is probably like the simplest case you could think of in this particular scenario. Now, why might this come up and where might this come up? So one of the cases we were thinking about when we started this work was clinical trials. So the example we look at in the paper is some COVID-19 data, where, as many of you know, the impact of COVID-19 is typically much worse on people that are older than 65. And so when you're designing the clinical trial, you have to decide who's going to be in it, which in our case is going to be the states or the contexts. And so we need to think about both what treatment or control are we going to give to each of those individuals, as well as what are the individuals we're going to include in our trial. So clinical trials is clearly one case where we could start to think about this question of selecting contexts and actions in order to make decisions. But it actually comes up in a lot of other cases. So many of you are working on LLM alignment. There was a whole RLHF session on this earlier today. And normally when we think about RLHF, we assume that we get access to some prompts and responses, and then we get some preference ratings. And typically we assume that those prompts just come from somewhere, maybe from the internet, maybe from some random data set. But in reality, we could actually pick which of those prompts we ask people about. So we could choose what the weighting is of things like news versus versus products. We could decide on sort of the composition of the topics we're going to get feedback on. And so that's another case where we actually do get to pick the context compared to the normal standard reinforcement learning setting, where the contexts themselves sort of come from the ether. Now this comes up in lots of other areas too, things like political ad targeting and many other areas or places where we do actually have this additional affordance where we can pick the states. And indeed, you can think of this as actually being related to the teleporting robot scenario. So there's been some work around sort of like the late, 2009 to 2015-ish, of people thinking about RL, a multi-arm bandit learning, with a generative model. So this means that you can ask about any state and action pair that you want to and get a reward back. And people often jokingly call this the teleporting robot scenario, because it's like you can just take your robot and put it in a state, make it do an action, and see what the outcome is. So of course, this is not always possible, but in some cases, we really might have that affordance. Things like when we have a simulator, you can often sort of teleport it into an emulator of an Atari state. And what are the sorts of capabilities that might allow us to have? So how are we going to evaluate how good is a policy when we think about this? Because we're going to want to use that information to decide what data we should gather. So what we're going to do in this case is we're going to look at the expected regret over states or groups. So imagine in this case, again, we only have a very small number of states. Let's just say over 65 and under 65. And what we want to know is when we extract a policy that is specific to each state, should we give over 65-year-olds the vaccine or not, and under 65-year-olds the vaccine or not, how good is the resulting decision policy? And we're going to compare that expected regret, the expected performance, to what is the best policy for those groups, which is unknown. So we're going to try to optimize this. This is just how we're going to evaluate a particular policy. So in particular, what the problem setting that we're in is we want to think about how do we gather data to minimize this minimax expected regret. So what I get to choose in this case is who do I give samples to, how many older adults and how many younger adults, how do I allocate them to treatment or control, or to the two actions I have. Now in this case, because the actions are only two, and we're assuming no function approximation, once you decide to give samples to a particular group, you should just do half and half between the treatment and control. So really the only main decision here is what is the proportion of groups you're going to use in your experimental design. So this is saying how many samples do we give to each state or group. And we want to do that in the following. We want to do that such that when an adversary comes along and picks the reward function, which is how exactly good is this vaccine for older adults versus younger adults, then we want to minimize that expected regret. Now I want to highlight in this case that we're weighing the rewards by the state or group proportions. So that means that when we finally evaluate this policy, if most people are younger, they're going to contribute more to the performance of our policy. So the question in this case is how should we break down this sample allocation? Now, how does this compare to sort of the normal reinforcement learning or multi-arm bandit setting that we often think about? So normally in reinforcement learning, we assume that the states come from some sort of stochastic process. We still compute a policy per state, but we often do things like pack learning, where we try to find the optimal decision for every single state. Or we might use that data for something like hypothesis testing. In contrast to that, I'm thinking of a slightly different situation where we actually get to strategically sample the states in kind of this teleporting robot way. We're still going to compute a policy for states, and then we're going to aim to optimize this expected performance weighed by the probability of each state. That is the probability, someone is older than 65 or younger. Now, for those of you that are familiar with pack learning, you might say, well, if we get a near optimal performance policy for every single group, won't that automatically be near optimal for the whole population? And that's true. So it is sufficient to do pack learning, because if you do pack learning, you're automatically going to get a really good performance policy for the whole population. The question is whether it's necessary and whether we can do better than that. And in particular, the question that we really wanted to look at in this case was, is proportion population sampling optimal? So remember, that's what we normally do. We normally assume that states are just coming in, and then we just make decisions for them. And so those will be generated by the underlying population proportions. And so the question is, can we do actually anything better when we can strategically select the states? Should we do something different than population proportion? So that was the main question that we wanted to think about when we came here, because that would suggest that despite decades of literature on things like clinical trial design and pack learning, et cetera, that maybe there was a different thing that we should be doing when we now have this new affordance. And perhaps surprisingly, it turns out that the thing that actually optimizes minimax regret is not proportional sampling. Okay? So if you assume that you have a finite budget of samples, you have 10,000 samples to try to decide whether COVID-19 vaccines are good for older adults and younger adults, you should not allocate them according to the population of older adults and younger adults. That is not going to minimize your regret. So in particular, what we found is that the way you should allocate them is to allocate more to whichever groups are smaller at this kind of 2/3 rate. So you should upweight the smaller groups. And it turns out, after we published this paper, we found that actually there was another paper from a different community which had also found this, but for a different setting, where they were trying to just minimize an upper bound to the minimax regret, and another paper that looked at this for a 2-context case. But to our knowledge, we're the first to prove that this actually optimizes minimax regret. Now you might be sitting here thinking like, well, why is that? Why shouldn't you, ultimately you care about this average regret at the end where you're going to weigh contexts according to their probability. So let's go through a little bit of intuition for this. If you think about what we want to do in this case, the probability of us making an error is going to be because we estimate the reward wrong. So we really care about how our uncertainty over the reward is changing as we get data. In many ways that we quantify uncertainty, the rate at which our uncertainty decreases is at 1/√n. What this means practically is that getting the 101st sample for one context is not as helpful in reducing your uncertainty over the reward uncertainty compared to the 10th sample. Okay? So sort of intuitively, if you have multiple different groups, it is not as valuable to get many, many more samples for the larger group as it will be to get a few more samples to the smaller group. So that's sort of the intuition for why we can prove this is minimax regret optimal. So you might be sitting here thinking, okay, well that's interesting. Maybe that's obvious in retrospect, as is much of science. But almost everyone does do this proportional sampling thing. So was that actually justified? Like, were there cases under which that was actually the right thing to do, that we've been doing this all along? So we actually also proved that this is optimal if you just get to make one decision for everybody. So in the standard sort of setting, if you're just going to decide I'm going to give a vaccine to everybody or nobody, then actually you should do proportional sampling, and that minimizes the minimax regret. And so what I want to highlight in this case is that as we move into many more scenarios where we could do personalized or context-specific decisions, we need to rethink how we do experimental design, because we have these new affordances that mean we should change compared to sort of the standard paradigms. So what does that look like in the case of an application area? Well, we looked at this data that came out of the one of the COVID-19 trials. And this is the allocation we would get for, there's roughly 10,000 people in this particular study. So we would say you should give about 6,000 to the younger group and about 3,200 to the older group. And this is what we would calculate would be the mini-max regret. Compared to the normal approach, which is you just sample according to the populations, which means you'd give way less samples to the older group. And in fact, you would get worse mini-max regret as is satisfied by our theory. Now, again, note in this case, it's that we're changing how we put samples into our experimental group. Ultimately, we're still trying to just optimize for this overall expected regret, where we still weigh individuals according to the probability of their groups. But of course, one of the side benefits is that if you actually allocate more samples to the smaller groups, they're likely to get better decisions too. And so in this case, we find that if you look at the worst regret over the groups or the contexts, you also get a gain. And this again should be natural because for that group that's over 65, you're giving them a lot more data, which means for them, they're likely to have a much better decision at the end. So I think it's quite interesting in this case that you would actually just get sort of a win on both of the objectives you might care about. You get a win because you're more explicitly optimizing for this mini-max regret over the population. And you get a win for the individual contexts as well, because you are making better decisions for each of those instances. So I want to highlight in this case that this is just one example of a place where, despite an enormous amount of really beautiful work thinking about how we should gather data better, there's actually still a lot to be done. There's still these underexplored settings, which are starting to come up as we can do more and more personalization, that mean that we actually need to re-examine how we should gather data. And in doing so, we might be able to do much better than what has been previously possible. So the second thing that I want to talk about is how do we use data better? So the first thing I was talking about is if we could gather data, how should we gather it? And then the second question is, once we have that data, how do we squeeze the most we can out of it? And this is related to what Finale was talking about as well. So I'm going to give an education example. This is an educational interface to teach students about volume. In this case, the kids get to go on various quests, and as part of that, they have a nice avatar that can help them along the way when they're solving different challenges. So in this case, if the student gets stuck, they can ask for feedback or support from their avatar to help them learn and solve the problem. Now, I just want to highlight here, this is pre-2023 LLM chat, so we can no longer call this a chatbot because people have very inflated expectations. But we did use sort of a simple rule-based approach, and we used hierarchical reinforcement learning for this. So the idea in this case is we pre-specified different types of low-level policies around different ways of supporting kids as they try to learn things. Things like acknowledgement, encouragement, guided prompts and questioning, or direct hints. And then what we wanted to learn from reinforcement learning is when do we do each of those sort of options or sub-policies in order to help the student learn the most. So we had a setting here where students would do a pre-test, they would interact with our educational interface for a while, and then they would do a post-test. And what our goal was is to change the policy of how the avatar could help support the student in order to lead to better gains in terms of the post-test. So we started off doing this as an online reinforcement learning setting, which means that we would have students use the software, and then as we saw their results, we would change how the software was teaching the next students. And when we did this, we were doing this during the pandemic, and it was extremely difficult. Okay, so we got about 200 trajectories, which means 200 students went through this, and it was an insane Herculean amount of work for the grad students involved. So as you can imagine, we have to recruit students, we have to set up Zoom sessions, we have to train them, we have to make sure that everyone goes through it in order, we have to take that data and immediately propagate back through reinforcement learning. And we are incredibly proud we got to 200 trajectories in this case. Now, unfortunately, as you're probably familiar, 200 trajectories is not big data. So what we wanted to think about in this case is that after we had gathered all this data, and we were sure we had not optimized the whole system, what could we do to kind of leverage that data better in terms of offline reinforcement learning to try to see if we could learn better decision policies. So to do this, we really dove into offline batch reinforcement learning, which is an area that my lab has worked in for a long time, and including with a lot of wonderful collaborators in the audience, and many of you as well work in this area. And what we wanted to do in this case is to take a data set and confidently produce a high-performing policy, if that was possible, given the data that we had. And one of the really big challenges in this case for us is that we were extremely data limited. So in particular, we can think of this as this general offline reinforcement learning problem where we had two components. These are the two most studied things in offline reinforcement learning. One is offline policy learning, where you take data and you're trying to learn a new policy. The other is offline policy evaluation, where you take data and a policy and you try to say how good it is. Now, for any of you who have not worked in offline reinforcement learning before, you might say, doesn't the thing on the right already do the thing on the left? And unfortunately, it's been shown by a lot of wonderful colleagues and some of our own work that normally, particularly if you're using value-based approaches, et cetera, the agent's own estimate of how good it is wildly optimistic. So it would think, the students are going to be math geniuses after 2 seconds. And in reality, the policy would perform very poorly. So we normally cannot trust the estimates that are being generated directly from the off-policy learning, and we need to have a separate way to validate those if we're in these high-stakes scenarios where we really want to make sure this works before we go through the pain of doing another 2-month trial. So how do we do this? Well, there's an enormous number of methods throughout this community on both of these types of things. And in this case, we were really looking at it more from a practitioner perspective, which is I did not care whether we were going to use BCQ or MOPO, et cetera. I didn't care which off-policy method we're going to use, importance sampling, doubly robust, et cetera. I just wanted to get a good policy that when we deployed it, we could confidently think this was going to help kids learn. And this is a real challenge because there's so many different methods, and most of them depend on the hyperparameters. And we did not have a simulator of students to go check all those different hyperparameters on. We were going to get one shot after this to kind of deploy it and to see how well it was working. So we were really trying to answer this question of how do we design a full pipeline to think about sort of towards an era of like off-the-shelf offline policy learning that we could take in a small data set and output a policy we thought would do well. Now, one thing you might think about is that we've all done machine learning classes. Let's just split the data. So we're going to take our data set, we're going to split it in half. On half of it, we're going to do policy learning. We're going to take whatever policies we get out, and then we're going to pick your favorite one or more policy evaluation methods, and then see which one looks best according to that, and then go. So we tried that. And we formed a whole bunch of different policies, with different algorithms and hyperparameters, et cetera, and we did this pipeline. And again, remember, we're in the small data regime here. So we looked at this from a sepsis simulator that came out of David Sontag's group, which is a simulator to sort of try to capture some of the different things in healthcare type challenges. And we looked at the small data regime, because remember, in our setting, we had 200 trajectories. So here we were a little more generous and we gave ourselves 1,000. So we did this whole pipeline, and what we found is that the policy that was being selected from this process, the sort of algorithm hyperparameter policy process, was not very good. So we did this whole thing, it did not work very well, and we got policies that would perform far worse than we thought was possible. So we thought, well, that's unfortunate, but this wasn't maybe the best. It was a single train test split. So we tried some other ideas. We tried bootstrapping, and we tried cross-validation. And again, to be clear, if you have more data, there is good reason to believe that some of these methods work very well. There is prior work that shows that these methods can work very well in other settings where they tended to evaluate them with substantially more amounts of data than what we're looking at in this context. So we were trying to think about, why is this happening? What is the problem in this case? So I always like to try to think about the smallest simple example that helps me to understand things. So let's think about a really small example. Let's imagine there's just two types of trajectories. There are good trajectories and there are bad trajectories. The good trajectories get high reward. The bad trajectories get 0 reward. You have a small amount of data. You're now going to partition that data into two sets. The training one, which you're going to be using for off-policy learning, and the validation one, where you're going to evaluate your policy. So you can only learn a good policy if your training data includes some of those good trajectories, because otherwise there's no signal to learn from. Everything is zero. But even once you get a good policy, you can only evaluate that it's good if your validation set includes those good trajectories, because otherwise everything's zero and all policies look the same. So you really need to make sure that those sort of good examples are both in your training set and your test set in this case. But when you're doing random partitioning, and when you don't always know in advance exactly what it means to have a good trajectory and a bad trajectory, this gets a lot more complicated. And what we proved in this case is that sort of intuitively, if you only do one split, and the amount of good data is pretty small compared to the amount of bad data, you have a finite probability, a sizable finite probability of not picking the right policy, because you're not going to be able to both learn the good policy and evaluate and know that that policy is good when you just do a single train test split. Okay, so that seems concerning because that's the sort of normal approach that we do, but is there something different we can do? And how does this relate to cross-validation failing? So it turns out that cross-validation can be particularly bad for this, because for cross-validation, we normally split our data into a set of sort of shards, and if one of those shards is really small, the chance of us having good trajectories in there out of our 200 trajectories is pretty low, which means that cross-validation is often going to fail. In contrast, we can use this method that's been around for roughly 35 years from statistics, which is just we repeatedly split. We just do lots of just like train test splits, and we do this many times and we average over it. Now, as some of you guys might notice, in this case, this means that our train and test splits across those are not independent. They can be correlated. But we can relate this formally, not us, but it was already known, to this being a sort of a leave K cross-validated approach asymptotically. And empirically, we found some enormous benefits. So in particular, we found that this sort of simple approach of repeatedly doing splits allowed us to learn policies through this whole pipeline of algorithm, hyperparameter, learning policies, and then evaluating them, that was far better for the same amount of data in this domain. Okay? So this is a really simple insight that shows that like, if you've got small amounts of data, the way we should use this data might be a little bit different. So you might think, okay, well that's just sepsis. I haven't ever heard of that. Are there some other benchmarks that this worked on? We also use the common D4RL benchmark, which a lot of people do offline reinforcement learning with, as well as the RoboCop Mimic, which was a robotics data set. And in both cases, doing this sort of repeated splitting allowed us to identify policies that were much better than the alternative approaches. So you can think of this really as being kind of this meta approach of how would we develop a whole offline RL pipeline that allows us to reliably find good policies for future use. And we use these ideas for learning the tutor policy. So again, we took our 200 trajectories and we tried lots and lots of different policies, but we did so in a way so that we could use the whole pipeline to then evaluate which of these we thought were promising enough for practice. We then ran we finally, after we'd done all of that and we were fairly confident, we did a new experiment with two conditions. So in this case, we had one condition in which the student didn't have access to an avatar, they didn't have a narrative, they just did the math problems. And in the other case, they had this narrative and they also had this specific helpful like reinforcement learning case. And in this case, we'd done some prior work to suggest that we don't think it's just the narrative, we think there's the reinforcement learning and the narrative is really critical. And then we ran our study. And the thing that I found really exciting in this case is that when we looked at dividing the students that took part in our study into low performing, medium, and high, it was the students who were lowest performing that benefited the most. So that suggested that we weren't sort of creating an AI policy that was making the rich get richer. We're actually finding ways to engage and support the students that weren't being helped before, and that this RL policy was significantly able to help them learn a lot better. So I think if we pop back, what I wanted to highlight here is that when the data is limited relative to the complexity of the problem, we still really want to think about how do we design these pipelines and these algorithms. And I found that David Silver's answer to one of the questions this morning really touched on the same thing, which was, he was asked then, why is MCTS better than, say, TD learning, when sort of asymptotically we'd expect in all of these cases we could learn the optimal policy. And his comment, which I thought was great, was saying, well, when the problem is so large, even we have lots of data, we still have to think about algorithms in that case. And I think the same thing is true in our setting, except for we have much less data, to think about when the relative amount of data we have to the complexity of the problem is imbalanced, then having clever ways or insightful ways to try to extract as much signal as we can is really important. And I think there's a lot more to be done. All right, the final thing that I want to talk briefly about is data, data, data. So we've seen some just sort of extraordinary advances by the formula of data plus compute plus big models. I mean, we've seen this in Atari and AlphaZero and large language models. It's really just, we've seen this over and over and over again. But one of the challenges there when we're making sort of sequential decisions is that we really need to be able to generate data. We need to be able to sort of simulate the world, or we need to think about multiple steps. And while that's possible in Atari, so far at least, we and many others have found it really hard to do that for a lot of societal focused domains which involve people. So things like education and healthcare, we've typically had to rely on real time and real people's data. And that's just extremely hard to get. Even if we have electronic medical record systems, those are from particular policies. There is rarely random data in them, for good reason. But it means that sort of doing the type of exploration that is possible in something like Alpha Tensor has been really hard to do in education. So this has been something I've been thinking about for a long time. And then, of course, large language models came along. And a lot of people started to think about, well, can we use large language models to simulate people? It's really hard to do school studies and to do healthcare studies for good reason. But what if we now could just have large language models be people? And then we could do things like optimize education or do all these other amazing things because we don't have to worry about the wall clock time and the real people that we're interacting with. And what I've shown here on the right is an example from some of my colleagues where they were getting these sort of simulated societies based on using large language models as simulated people. And they could do things like plan Valentine's Day parties and other things like that. But I wasn't sure yet whether or not they would be able to simulate how real people learn. So this was some work that we started doing a few months ago, where what we wanted to do is to say, well, could we actually use large language models to become our simulator and actually improve educational instruction through large language models, taking the place of trying to gather this really painful data. So the first thing we did was to say, well, if we're going to do this, we're going to need to see how good large language models are at simulating students. And we would do prompts like the following. We'd say, you are an 8th grader, and you have not learned anything about systems of equations. Solve this problem and give me the answer. And actually, it was pretty good at this. I mean, most LLMs can solve this problem, and it could pretend to be uninformed for a while. And so if we told it was a 5th grader or a 2nd grader or a 12th grader, it could do a decent job. We could do something that was plausible. But the next thing that we asked it to do was a little bit harder, which was to simulate the dynamics of learning. And this is what we really thought we needed, right? We thought this was going to be our transition dynamics. It was going to say, you're going to start off being this 8th grader, and then you're going to get some action or instructional intervention. So you're going to see a video, and this is what the video contained. Or you're going to do these 3 problems. And then after that, we would ask it to then try to solve another problem or to do something else where you would expect that its state should be improved. So I'm just going to make this interactive for a second. I'm going to ask you to vote whether you think that it's going to do a good job on this, whether the LLMs can simulate learning or not. So raise your hand if you think that the LLMs did do a good job at simulating learning. Okay, a few people. Human learning is what I mean. Okay, and then raise your hand if you think it didn't. All right, yes, well, so wisdom of the crowds. Yeah, it did a terrible job. So I love the optimist, though, in the room. Hopefully will be with you in a few years. So it did a terrible job, and as you might expect, after it had seen one thing, it was wildly optimistic. It would be like, yes, I can solve that problem. I can also do multivariate calculus. So, it sort of would forget that it was supposed to be an 8th grader, and it would just immediately revert. So this is a little concerning to us because we wanted it to be a simulated student. And if it can't simulate the dynamics model, well, how are we going to do RL with this system? So we were a little disheartened by this for a moment. And then we tried to think about, well, how do people actually design content. And for many of you in the audience, you probably also teach classes, so you'll resonate with this. So one way we try to design pedagogical content is we do studies. We do a randomized control trial, and we do things like, is a worked example better than a video? Or is reading a book better than doing worked practice? And we run a randomized control trial, and then we see the results, and we use that data to figure out how to do instruction better. So that's one option. We almost never do that. What we normally do is we just have an education expert, or even non-expert in some cases, make some instructional choices. So they'll say something like, okay, well, I think I heard this learning theory that worked examples are more helpful, so I'm going to include that. Or I think pair, share is supposed to be helpful for my students to learn, so I'm going to do that. And these are normally educational experts that have some backing in instructional design or in educational sciences. And so they use this to make decisions over instruction. And so when we thought about that, we thought, well, maybe we should move away from thinking of having an LLM to be a student, and maybe we can have them be an instructor. So we're going to move from having an LLM to try to simulate the dynamics of the world to trying to simulate how good do you think it would be if we did this? How much would it help someone learn? Now, when you first think about this, it may not be obvious whether that should be an easier question. So on the right-hand side, we've got an LLM that we hope would simulate the dynamics of the world. What happens to a student's knowledge state after they see some video or do a problem? But the other thing we could ask, and this is what we did ask, is we said, what if I was to give this action? How do you think the student would perform afterwards? And so here we're kind of marginalizing over that dynamics model and asking it to project and say what the reward might be or what the score might be. And we weren't quite sure how well this would work, but we decided to try it. And we sort of had prompts like this, which was saying, you have the same 8th grade student, but now you're not the 8th grade student, you're a teacher, and you're going to predict the probability that a student can answer a question correctly. Okay? And the goal was, if we could do that, then maybe we could optimize instruction with that, because then we could still essentially get some signal for how well our instructional designer, that was an LLM, thought different materials would be effective or not. So due to time, I'm not going to go through all of this part. I'm happy to point you to the paper. One thing we want to do first is to say, well, do we think that these LLMs can simulate anything about what an instructional designer would know? And so we used it to simulate whether or not it could predict standard results in instructional design. Now, we only did 2 studies. There's a huge wealth of research out there, but we did find promising evidence that it could replicate some well-known results in what is good pedagogy. And so we thought, well, okay, maybe this is a reasonable thing to try. We'll try it a little bit. So the key thing then is that what we want to do is optimize instruction. So what we're going to do now is we're going to say, we are going to try to optimize over worksheets to teach systems of equations. So this is language. We're going to try to, this is a whole worksheet. It could do anything in it. It could tell a story. It could give math problems. It could do anything that's, can be written in text. So this is an absolutely enormous action space. And we want to do the following. So far what I've been saying is that we would now have an LLM that we think might be okay at trying to estimate how effective a particular, say, worksheet or educational intervention might be at helping someone learn. And now we're going to close the loop, and we're going to have another system that says, okay, that's my reward signal. How am I going to change my worksheet, which is language, whole sheet of language, to try to change how I teach such that my LLM evaluator will say that they think that's better. So our first question was, is there any signal here at all? Okay, so do we even think that, does our LLM evaluator even think that we're doing a better job at trying to generate instruction? So a little bit surprising to us, it did. So here on the x-axis is learning iterations. It's like each time it's trying different worksheets, and then it's giving it to its LLM evaluator and saying, do you think this is going to help people learn more? And over time, it's actually learning to produce worksheets which the LLM evaluator thinks are better. So that's great, our system thinks it's doing better. But as David talked about this morning, this is completely possible that it is hallucinating or, over-optimizing, et cetera. So what we did in this case is we recruited 95 education experts, and we asked them to evaluate the LLM worksheets. So we would say, which of these 2 do you think would actually help kids learn better? And so we did that with lots and lots of pairs, and we could use that to learn a preference ranking. And kind of amazingly to us, the human education expert evaluation was really well correlated with the LLM evaluation. Okay, so in particular, the human preference score of which things they thought were better or not, and then we learn across those to order the rankings, is pretty related to what the LLM predicted post-test score would be. Meaning that on average, if the LLM said, we think this is going to help the student learn more, the human experts were like, yeah, we think this is also going to help the student learn more. So this was really surprising to us and suggested that there is a potential in this case to start to use LLMs to simulate aspects of human performance that could help us do things like optimize education. Now I want to put in a caveat here. Though they were strongly correlated, they were not leading to the same optima. In particular, human experts thought that all of those things in the circle there were roughly the same. They are like, okay, all of those worksheets are pretty similar. I can't really distinguish them. Sort of like when you're at the eye doctor and they're like, is A or B better? And you're like, it's kind of the same. So in this case, they thought that all of those were roughly equal, but the LLM thought some of them were much more effective than others. So it's not perfect, but it is enough so that you could see that things that the LLM thought were really good, even according to humans, were much better than some other worksheets. So there is signal there, even if you can't trust the full optima. So I think what this suggests in this case is that maybe if we're trying to move to a case where we think of ways to sort of synthesize data or get around having to interact with humans for all the human societal domains we'd like to tackle, we don't necessarily have to move all the way to things that can simulate the full dynamics of cancer treatment or student learning, but maybe there's some different ways to do data synthesis that can leverage these new type of tools in a way that we can start to use them for reinforcement learning. And I think in particular, I think there's this huge open question over how do we use this sort of amazing data plus compute plus large model approach, which has led to some really transformative results in lots of other domains, and think about how we can use it in the case to tackle things in medicine and healthcare and other settings which so far have been really hindered by the fact that we've had to rely on really slow-moving, painful data processing, data collection strategies. So just to summarize, I think that it's a really amazing time that we're in right now. I think that there's an enormous number of places where we could really benefit from better data-driven decision-making. And I think by making progress on this area, we could lead to a new era of helping people flourish in brand new ways. Thank you.